Hello, my name is Amir Nazari. I am a PhD candidate at Clemson University, Department of Automotive Engineering. Today, I am super excited to present our work on the implementation of accurate hydrologic connectivity detection using advanced transformers technology. Hydrologic connectivity plays a pivotal role in understanding water flow and overall ecosystem interaction. So we focused on leveraging advanced transformer-based models to improve the precision of detection of this kind of connections across landscape. In addition, we investigated the optimal TPU architectures to significantly reduce prediction latency that is essential for real-time application of hydrologic analysis. I will walk you through the methodology, results, and the future potential of this work in the next few minutes. Let's begin. So, as the outlines, I will first start with problem statement and motivation, followed by data collection and pre-processing techniques. Then we propose detection transformers, in short, DETR, as a solution to hydrologic connectivity task. Further, we go over the detection, inference, in post-processing techniques, and finally we finish by the introduction of hardware acceleration technologies comparison. Let's get started. So accurate detection and localization of hydrologic connectivity is a key for managing water flow, sediment, transport, and ecosystem health. However, this is not an easy task for a simple object detection technology. So first of all, the image that we used is a large landscape with complex terrain, and furthermore, the image source is the LiDAR-based high-resolution digital elevation model, or in short, DEM, that mainly suffers from measurement, noise, and varying data modalities. So our motivation for this project is the introduction of transformer-based models that are known to be effective and offer superior performance in complex visual tasks, and apply it for drainage crossing and hydrologic connectivity detection and localization. However, transformers are pretty slow compared to their competitors. So therefore, by optimizing the model and using the different configurations of TPU, so we will propose the best optimal architecture that help us improve the inference of the model. So the data set that we used is LiDAR-derived high-resolution DEMs, so which is roughly about 6,000 of georeference TIF rasters, each 800 meter by 800 meter footprint, and with the resolution of 1 meter by 1 meter. So the elevation in meter above sea level considered, and the 32-bit floating points are associated to each of those TIF rasters. So data source is coming from USGS 3DP program, and so the current data comes from 4 watersheds in the US, one in California, in Illinois, in North Dakota, and in Nebraska. So the data set of drainage crossings as a main part of hydrologic connectivity task is primarily unlabeled. So our first task was to create label for whole data sets. So we label each crossing as a centroid bounding boxes of 100 meter by 100 meter created around each drainage crossing object. Furthermore, we converted the data labels into COCO format, which is essential for DETR models. So final data set contains about 6,000 DEM chips after filtering of no data and anomalies values, and overall more than 13,000 of bounding boxes for drainage crossings. So we consider Maple River in Nebraska reserved for transfer learning experiments. And finally, we did inclusive data augmentation during the training by doing the random flipping and cropping to enhance the model generalization and performance. And finally, we did the validation by the center cropping of each image. So DETR has several key advantages over traditional object detections. So first, there is no need for handcrafted components, such as what was in faster RCNN or ULO. So therefore, it enables us to have and come with an end-to-end training pipeline. Second, transformers benefit from extensive transformer component that is the self-attention mechanism. So that is a key. So self-attention mechanism has shown to be effective in capturing complex and long dependencies, so which is the best case for our use case. And also the overall architecture is much simplified, is more simplified than other competitors. So in the sense that there is no RPN or non-maximum suppression components named NMS and so on. So as the experimental setup, a recipe, so we did object detection experiment on several input sizes variations to assess how they affect the model performance. So the different input size and their corresponding cropping strategies are as followed. So we used 800 by 800 images, that is the original size, therefore there is no cropping applied. Next, we had 600 by 600, then 400 by 400, and all the way down to 256 to 256. So these images were randomly cropped to create different variations in the training during the training dataset augmentation. So despite these variations in input size, we ensured consistency across all experiments by keeping the hypoparameters, model sizes, and all other constancies. So all experiments were executed for 500 epochs to ensure the sufficient training time and model convergence passed. So for validation and testing, we used center cropping to ensure that all validation and testing sets were comparable across experiments. However, due to the different cropping strategies during the training, the validation, and the testing set do filter across different size variation. So this introduces a challenge in directly comparing results, but we were able to account for this through the careful setup and evaluation recipe. So this setup overall allowed us to analyze how different image sizes and cropping strategies impact the model's ability to capture hydrologic connectivity. Next, we do the training, validation, and get the results. So we used key statistics for model performance, so as average precision or AP and average recall or AR, and we did this for a different IOU. So as we can see in this table, so starting from 256, we increase the size all the way up to 800 by 800, which is the full image. And so we did the training with two different recipes, so the initial and the transfer. So initial is the one that we use the model as it was, and then we just retrain the whole model on the data set. But the transfer is, so we use the pre-trained parameters and just retrain or fine-tune the model on the transfer data set. So like we can see, actually the best results both for AP and AR were achieved once the size of each image is at its maximum, the full image, and with the initial recipe. So this is the indication of first, so the more the size is, the more inclusive and information can be extracted from that. And so somehow by having the smaller, like a larger crop, so we are losing important contextual information. And furthermore, it shows that the transfer learning was not as successful as retraining. So that might be because of the notion that the pre-trained model is trained on COCO dataset, so which is essentially very different by nature than the dataset of LiDAR-based DEMs that we used. So therefore, starting from scratch gave us better performance. And so we can get the demonstration by observing this visualization. So the model outputs from the initial test set are shown at the top, and the transfer learning one is from the test set shown at the bottom. So as we can see, by reducing the image size, so we can see that the model fails to accurately identify and localize the culverts. So the green is ground truth and the red is the prediction. All right, so despite outstanding DETR performance, so we mentioned that these models are pretty slow compared to other competitors like ULO and faster RCNN. So like we could see in a table that the original authors compared, so we can see that despite the higher accuracy and smaller parameters, so still the training and inference time of DTR model is higher than the faster RCNN. So therefore, our objective is to accelerate the inference and reduce the detection latency. So now the question is, what is the best hardware acceleration technology, TPUs or GPU? Well, by taking a look at the benchmarking table that compare different architectures and models. So for the TPU and GPU, so we can see that the TPU leads superior performance compared to GPU in both transformer architecture and ResNet 50 models, so which are the fundamental and key components of DTR. So therefore, we're gonna stick to a TPU for the rest of our application to reduce the detection latency. So accurate simulation of TPU hardware architecture and mapping strategy is a challenging task. So the solution is use of a scale sim, that is a state-of-the-art tool for cycle accurate deep learning models workload simulation. So there are several benefits of scale sim. So first of all, it is compatible with industry standards systolic arrays architecture. It offers accurate derivation of total inference latency. And finally, it is reliable in terms of performance estimation. Now the question is, so what is the optimal TPU architecture? So our problem is to find the optimal match between the hardware architecture and mapping strategy that minimizes the DETR and inference latency. So our solution to this problem is to create genetic algorithm using PyGAT framework combined with scale sim performance estimation tools to find the optimal TPU architecture. So our objective is to minimize the total latency time of inference in the genetic algorithm optimization. So we define the gene space for the genetic algorithm. So we define 8 different genes as one chromosome, and so we can see the chromosome structure here. So one is systolic array width, systolic array height, input feature memory, weight memory, output feature memory, bandwidth, memory banks, and mapping. So for genetic algorithm properties, so we use 50 generation for parent chromosome, 10 solutions per population, 8 genes per each chromosome, and finally the fitness value is total latency. So we used Google TPU version 3 as a baseline for performance comparison, and we did a couple of different recipes and design to get the best architecture. So in the table, we show that the lowest delay solution offers significant latency reduction, but of course, it requires more resources. However, average latency solution provides a balance between the performance and resource usage, so that can outperform the baseline TPU. And finally, for the future direction, so we're gonna use more advanced and emerging transformer technologies, and also making a higher degree of data augmentation techniques. And finally, we're gonna use more advanced TPU architectures by developing more advanced TPU architectures that specialize hardware accelerators for metrics multiplications and other key operations. Thank you so much.